Okay, so first of all, I'd like to thank the organizers, Patrick and Barbara, to give me the opportunity to speak here. And well, I'm finishing the meeting by a different topic, I guess, because I'm going to be speaking about another part of the Earth. I got a review recently that said we know enough about the mental and should shift our focus elsewhere. So I guess I'm going to shift my focus somewhere else, to the inner core. And so I'm going to show you some work we've been doing with people in Grenoble. So I'm speaking today, but really the work is a collaboration with, so he was a PhD thesis, mostly a Faino Alinco, that was co-supervised with Philippe Cardin in Grenoble, and with input from Renaud Desgain in Lyon. So the Earth's inner core, so it's a small sphere at the very center of the Earth. 1,200 kilometers radius, and there's many things that go on about the inner core. There's a big literature about it, but one thing that is relevant to this meeting is that there is anisotropy, which is that the waves that travel north to south are faster than waves that travel east to west. And that this structure is even more complex than that, with the outer inner core being isotropic, the inner core being anisotropic, and different between hemispheres, and a very complex structure. So how is it measured? I'm not a seismologist, but we're going to be using this representation. So so you have seismic waves that go through the inner core, and what seismologists do typically is they'll take the differential travel time between the waves that goes inside the inner core and the waves that goes inside at the outer core, not far from the inner core, to cancel the effect of the mantle and the crust. And then what you do is you plot this differential travel time as a function of this angle to the Earth's rotation axis here. And if you find something that depends on the angle, well, you have some form of anisotropy. And those are results from a paper from Jessica Irving, for instance. And so she's plotting these differential travel times as a function of the angle to the Earth's rotation axis. So this is north-south, this is east-west. And so the waves which are in this region are fast, the waves which are in this region are slower than average. And what is typically done is to fit these measurements with some form of a cosine square law, and this fit gives you an amplitude of anisotropy. And in this case, this author claims that there is 3.8% anisotropy in the inner core. As soon as inner core anisotropy was discovered, in the 80s, there has been multiple papers trying to explain why you will have such anisotropy. And so you will find articles describing thermal convections, some forcing from the outer core, some other papers explaining that the heat is extracted faster at the equator by the convection in the outer core, or that it's just a crystallization that's inducing this anisotropy. You also have papers that claim that there could be melt inclusions inside the inner core that gives you this anisotropy. So those are all like global models that gives you ideas of why it could be there. There are implications to that. Is that and what has not really been done in the past is there's been those models, but there's not been a correlation between the models and the actual observations, and this is really important because this is how you're going to constrain which model you choose, and so it's going to tell you something about the inner core structure and also about his history. All of those models depend on how the inner core was formed. I also want to point out something is that when we fit data with a sine square, with a sine curve like this, it's really a simplification because each of those purple dots here is a data point, and it's not noise that you see around the fit, it's just data, and it's just because it depends on the geography. So as a mineralogist, there are key questions we want to know when we want to look at the inner core. One thing is the crystal structure for the inner core iron alloy. We want to know about elasticity, and we want to know how do you get crystal alignment through, for instance, crystallization or plastic deformation. And even if you have your mechanism, you need to know how to model it. So how do you model that numerically? How do you calculate elasticity at all scales? So in terms of the phase diagram, from experimental point of view, I think the situation is getting sorted. At inner core conditions, iron is HCP. I mean, there's not been much. It's been, all papers converge towards that. But on the other hand, there's still issues. Like if you put light elements, you may actually stabilize other structure, and the energy difference between HCP and the cubic structures is small. So I'm going to show you some experiments. When we tried to do a deformation experiment on the HCP phase of iron, that's pretty old work now. So I'm going to go fast, where we were using either the Didaya deformation press to work at like 15, 18 GPa in this case to do deformation on HCP iron. It was done by Nori Nishiyama. And we also use a diamond anvil cell, which is not really a deformation apparatus, but from which you can develop activate plastic deformation mechanisms and say something about plasticity. At really high pressure, you can go to 3 megabar. And now we're actually working on doing it at high temperature as well, either with resistive heating or laser heating, for instance. One key issue when you do that, Sean already mentioned it, you need to do measurement in situ. So we go to synchrotron, measure the sizes of our sample, measure X-ray diffraction, get information in situ as the sample is being deformed. And those are typical experimental measurements. This is from a deformation experiment on HCP iron in the Didaya, where you measure the strain as a function of time. You can measure textures that develop in your polycrystalline sample as a function of time as you're deforming it. And then you measure the elastic strains from the X-ray diffraction at the macroscopic scale, and that tells you something about stress levels and plasticity in your material. When you have these measurements, the key is how do you analyze it, and we fought for a while for that, and now I think we have a pretty good solution. Is we actually go through a set of self-consistent polycrystal plasticity calculations. We really cannot do simple averages, and so we go through this process of iterative calculation with some hypothesis, but the parameters that we can play with are crystal structures, elasticity, plastic deformation, and the geometry with different approximations. And those codes are really important because we can use them to not only the interpretation of the experimental data, but also once we know how to we calibrated the codes based on experimental data, we can actually model the polycrystal behavior in any geometry. So I'm going to summarize years of work on iron in one slide. Where this is what came up from all of those high-pressure experiments. These are the plastic deformation systems that we find in experiments. Basal slip is there, prismatic slip, pyramidal slip sometimes, but also a lot of twinning that occurs at low temperature. And so when you work at low temperature in a diamond anvil cell, you find a lot of basal slip and a lot of twinning. And then when we did experiments in the Didaya, a little bit higher temperatures, and we saw the activity of twinning decreasing and activity of pyramidal syplice increasing. There are some hints that when you work at high temperature in a DAC, there's a lot more activity of this pyramidal syplice slip system, with still a lot of basal slip being active. And we have a full self-consistent model of the Didaya experiments. And so now, I'm not saying that the mechanisms that we have in the experiment are going to be the one in the inner core because the conditions are different. But at least we understand the plasticity of HCP iron in the conditions of the experiment, and we can build on from that knowledge. Those are new experiments, very new, with no result yet, but I think it's interesting, and there's going to be things coming out in the future, so I wanted to show it to you. Is we can now do dynamic compression on those HCP alloys. It's work we've been doing with Ariana Gleason, Cindy Bowman, and Wendy Mao. The idea is to drive compression with high power laser. You put a piece of polymer behind your sample, evaporate it with high power lasers, and that creates a shock wave. in the sample, and by playing, this is work of the Tom Duffy's group, where he was estimating what kind of pressure range we can reach by playing with different types of laser drives. And as you can see, we can go really, really close to the inner core conditions. We can actually go over them with this method. Now, as I insisted before, we need in situ measurements. And so this is what's being developed, for instance, at the MEC beamline at Stanford. And so the, I forgot to mention, oops, how do you go back? I forgot to mention one issue when you do this experiment is the compression range is you have about 10 nanoseconds to do your measurement. And so it's a bit quick to do diffraction. And so when you want to do diffraction in 10 nanoseconds, you have to go to an instrument called the free electron laser. This is a free electron laser in Stanford. It's a big accelerator that generates really intense pulses of X-rays. And the pulses of X-rays are on the order of 10 femtoseconds, and they are sufficiently, you have sufficient energy to create diffraction. And so the laser compression is in this tunnel here, and this is the free electron laser to generate the X-rays. That's inside the chamber. This is sample chamber. This is all the lasers for creating the laser compression. And when you go inside the target chamber, the targets are sitting here. Laser drives comes from the back, and this is all the apparatus to study the shock wave and collect diffraction data and so on. So this is very preliminary, but we can collect diffraction under those conditions. This is when you shock a sample of iron. This is BCC iron, and as you shock it, we can measure the transformation to HCP. At 4.5 nanoseconds, you have BCC plus HCP. 5.5 nanoseconds is pure HCP. 6 nanoseconds, pure HCP. And then you go back, you decompress. And so the good point is we can measure the phase transformations from BCC to HCP. And if you know a little bit about diffraction, you'll notice that there's textures, and I'm sure there's stress in there. So we can actually measure stresses and textures in such an experiment. So stay tuned, we're still fighting with the data. So how about the inner core? So the inner core, what we wanted to do with the, in our model is we wanted to understand the inner core anisotropy using a self-consistent model. We wanted to start from a crystal structure, a macroscopic model, crystal structure, plasticity, integrate that into an inner core that we're building through a numerical model, calculate the seismic properties at the local scale, and then propagate seismic rays through the virtual inner core and try to see if we can reproduce anything that looks like seismic measurements. So the objective was like, in the literature, as I showed before, we have a lot of those a lot of models, but none of them has tried that to see if you could reproduce the data. And we wanted to constrain, like, first of all, can we even get this 3% global anisotropy that is in the literature? Can we say something about the crystal structure, elasticity, deformation of the iron alloy, and what is driving the inner core dynamics? So this is where we move away a little bit from the experiments. We stayed open. We said we're going to try the cubic structure. If iron is BCC, if iron is FCC, and if iron is HCP, we're going to try all of those systems and see what comes out. In terms of deformation and how the inner core is built, we went for this model from Yoshida et al. in 1996 because it's the only one that really gives you a lot of deformation at the inner core level. You get like more than 100% deformation in such model. It's axisymmetric, so you're going to get a north-south anisotropy. And so this is a quality of this model. So what you do is you grow the inner core with time, and as the inner core grows, it's growing faster at the equator, and so it's generating a flow inside the inner core. And we crystallize iron at the surface and then calculate how the texture is going to evolve inside the inner core with time. We use several extensions. In particular, this is in this model, we assume that the crystallization at the inner core boundary is random. In this one, we assume that there was preferential crystallization, some crystallization textures, and this one assumes that there is some chemical stratification, and it makes a much stronger flow, concentrates the flow in the outer layer. So we built a virtual inner core. We have the flow field at all times and all points. And then we plug in our crystal structure. We use polycrystal plasticity models to calculate the textures at any point in the core nowadays. That's the present-day inner core. Then you plug in elasticity, and when you plug in elasticity, you can calculate the velocities at every point inside the core in 3D. The next step is to simulate a seismic measurement. So we choose random ray passes through the inner core, 300,000 of them, and calculate the travel times through the inner core, and then normalize it and plot it exactly like the seismologists will do. And this is the result. If you take BCC iron with those elastic constants, and this is the plot I showed before. This is the fit of the Irving paper. And this is the result for our simulation. Basically, you don't get any anisotropy at all with those hypotheses. If you say that iron is FCC, it's the same. Like with those elastic constants, you deform iron in this flow model, try to propagate seismic rays, and this is the residuals that you get. This is the measurement in the actual inner core, and it doesn't work. You don't get anisotropy at all. We also tried, so this is what that was the first series of models. We tried with HCP, there was basal slip, and we tried different elastic constants from the literature, and it was the same. Like we got something that was more anisotropic, but it was difficult to get to anything that was actually, that would be anywhere near 3%. And so after a few years, that took 3 years, it was pretty disappointed to get to that. The PhD student was getting depressed. And so we decided to extend the model. We had to do something. In terms of geodynamics, we were locked. Like our model gives a lot of deformation already, and if that doesn't work, it's going to be hard. We didn't try everything for HCP yet, so we have multiple choices of plasticity. And then we decided to just move away from the published elastic constants. Maybe that's the issue. It's really hard to calculate or measure elastic constants under those conditions. So we just did a Monte Carlo search for elastic constants that will work. How long do I have? 7 minutes? Yeah, it's fine. So yeah, we decided to just do a Monte Carlo search for elastic constants. He was just, since it didn't work, let's move away from what's in the literature and see what happens. And this is what we got for cubic iron. And so this is the global inner core anisotropy as a function of single crystal anisotropy. This is BCC iron, and this is a model with the inner core, the pure Yoshida model with the inner core crystallizing faster at the equator. This is the Yoshida model with the extension of chemical stratification, which makes a lot more flow, and same for FCC. You want 3%. With this Yoshida model, you don't get anything. You never get it. I have to say, all of the possible elastic constants for a cubic phase are in this plot. We tested 5,000 sets of elastic constants, and actually they all fall. You can all represent them with this single crystal anisotropy parameter. And if you put this complicated model that has also chemical stratification, you can have more anisotropy. It's possible, but still you don't get 3%. Even if this is as anisotropic as you can go for a cubic crystal. If it's more anisotropic, it breaks down. So whatever we did, it's impossible in this model, within this framework, within our hypothesis of plastic deformation, to get 3% anisotropy with a cubic crystal, with a cubic ion. It's just, it doesn't work. Whatever the crystal structure, whatever the plasticity, whatever the elastic constants. So it didn't work either. So now we moved on to HCP. And so HCP is more complex. You've got several axes and different subsystems. And I'm going to show our results on those maps. I'm going to show you a lot of them, so that's why I'm going to spend time explaining what those maps are. This is in color is the global inner core anisotropy. And we want to have something that is between 2 and 4%, something in the orange or red. And then this is something related to the single crystal, which I will explain now. In an HCP alloy, when you want to plot the velocity as a function of in the single crystal, you plot the P wave velocity as a function of orientation to the C-axis. This is the P wave velocity here as a function of orientation to the C-axis, and so this parameter here tells you which axis is faster. If this is negative, the A-axis is faster than the C-axis. If this is 0, they are the same. And this is positive, the C-axis is faster than the A-axis. And then the other parameter is to account for different shapes, like you can have some maximum in between, positive or negative, and then you can move and get any form, any shape of single crystal anisotropy with those two parameters. And basically it tells you how the velocity is changing as a function of the angle to the C-axis. So here is what you get. So this is the Yoshida model, where the inner core is growing faster at the equator, with dominant basal slip for HCP, with dominant prismatic slip, with dominant pyramidal C plus A. And what happens when you do dominant basal slip, it doesn't work. Like you get anisotropy, but it's the wrong way. If you put prismatic slip, you don't get anisotropy very much. The inner core remains isotropic. Now, if you put the pyramidal C plus A slip system being dominant in HCP ion, then you start getting a lot of anisotropy, and you get it, and it's the right order of magnitude, and you have many solutions. And this is so plotted, as a function of, so this is this difference between the velocities along C and A, and this the maximum at 45 degrees in the single crystal. So pyramidal slip is really a key ingredient to get anisotropy at the global scale. If you get the reason is that pyramidal slip is very efficient at aligning C-axis in an HCP alloy. If you use prismatic slip, because of the direction of the Burgers vector, or if you use basal slip, you don't get a good alignment. If you use pyramidal slip, on the other hand, the C-axis is aligned very well. So you can use different core formation model with dominant pyramidal slip. This is the Yoshida model. This is the Yoshida model with so the inner core growing faster at the equator with crystallization textures at the inner core boundary, and then the model with chemical stratification to concentrate the flow. And basically, in all cases, we actually you can find solutions which are anisotropic. Again, this is the anisotropy in the single crystal. All little dots here are sets of elastic constants we tried, and then the contours are contours of global inner core anisotropy. And so anything that is in red or orange could be reasonable. So I'm going to focus on this one, which is the one with chemical stratification, but I could use another one. So this is the solution. So we have many models where we can get 3 or 4% or more anisotropy in the inner core. And now, how does that compare, those elastic constants, compared to what was in the literature? Well, when we started the work, there was those two papers from Lidunka Vocadlo and Shah and Cohen. And so this is a Vocadlo paper, this is a Shah and Cohen paper, and they were finding very isotropic HCP ion at inner core conditions. But then afterwards, actually after we were working on that, the London group came up with the idea that when iron is getting close to the melting temperature, the elastic properties of iron are changing a lot, and actually as it is reaching melting, it becomes very anisotropic, and it goes right into the range that we need. Now, I was told by Daniele Antonangeli that he doesn't really like this pre-melting issue. But on the other hand, they've reperformed new calculation based on an advanced ab initio model. They're calculating phonon dispersion curves. And actually, apparently, they are getting into elastic constants in the right range. I think they're getting elastic constants in this range here, if I'm correct. And so actually, it seems like one of the issues was that iron is more anisotropic than we thought when we started. So, yeah, finally, we had one. Actually, we had many. Now we have too many solutions. So that's another problem. And so what are the take-home messages? Well, it's not so straightforward to build an inner core with 3% anisotropy. There are many models in the literature, but when you try to put them in equations and calculate seismic velocities, it doesn't work. And so one key ingredient is that the flow has to be simple. If your flow is too complex, everything is going to cancel out. Like it's not like in the mantle. In the core, the rays go through the whole thing. And so they cross from one side of the inner core to the other side. And that really cancels everything. We cannot get it with cubic structure unless it's 100% aligned. But then mechanically, I don't know how that happens. It's possible with HCP. We have many solutions. But you need activation of mechanism like pyramidal slip, which is very efficient at aligning C-axis. You need a fairly anisotropic single crystal, which was a surprise at the time. But apparently, we were not thrown off. And we were hoping to make a discrimination between our different core formation models, but at that point, at this point, we cannot. We can get all of them work finally at the end. And so that will be the next step, is to use the real measurements, entry and exit points, for instance, and try to see if we can make a difference between the models. Thank you for your attention.